This is chapter 3, and in this chapter we're going to be looking at stoichiometry and some chemical formulas. And again, this is some of the background information that you probably learned a lot about last year in regular chem. So starting off here, the first one we'll mention here is a guy named Lavoisier. And you can see he kind of lays the groundwork for the law of conservation of mass, which Dalton expands upon later on. And he really does some remarkable work in regards to stoichiometry. Where he's taking some substances of defined amounts and then determining or predicting how much he'll be able to produce. So he's really the person that gets a hold of the idea of stoichiometry, that if he knows how much reactants he has based on some ratios, he can determine how much of a product he's going to receive. So these chemical equations, that's him looking at the ratios. So he's looking at, well, if I have X amount of this and Y amount of that, I should be able to produce this amount. So he determines these ratios, and we've been able to prove it with a lot more sophisticated abilities today. So just an example looking at this, we'll break it into its parts here. Reactants, those are the things on the left side. They are reacting. And then you have products, the things that are being produced on the right side of the equation. The states, we typically list those in there because it can change the amount of energy we'll talk about later on. So these G's here listed here say that we have gases. If it was an S, they'd be solids. If it was an L, they'd be liquids, which is typically only written for water. And there we go. Coefficients, these are the numbers that we list in front. So the coefficient for that one is 2. For this methane here, it is 1. The carbon dioxide, it's not listed, it's 1. If it's 1, you don't have to list it. It's not wrong if you put it in. Subscripts, these are the little numbers down here. Typically, if you're doing any balancing on equations, you can change the coefficients all day long, but you cannot change the subscripts. The subscripts are permanent as far as a specific equation. Reaction types, this is a small listing of some of the different types of reactions that we could have. Here you have what's called a combination reaction, in which you're having two things added to make a new substance. So there we have a couple different examples of that. And then just the opposite, you have a decomposition reaction where you have a substance that is falling apart or breaking into two new substances. There's some other ones out there as well, as far as single replacement and double replacement reactions, but they're not listed here. Combustion reactions, typically you're having oxygen added to something and it's going to produce carbon dioxide and water. It doesn't have to, but it usually does. More importantly, it also usually produces energy. Formula weights. This is a simple example of that. Just the idea that, okay, what is a formula weight of calcium chloride? And this is an ionic substance. So typically we do this for ionic compounds. Calcium, I have one of them, so the formula weight off the periodic table is 40.08. Chloride, I have two of them, so I'm going to multiply the number on the periodic table, 35.5 or so, by 2, and then just add them up. And that gives me the formula weight. AMU is atomic mass units. And sometimes we just simply call that grams, because that's what we refer to for moles. Molecular weights. This is typically what we're talking about for molecular substances, so molecular, molecules. And the difference between formula weights and molecular weights is in formula weights in ionic substances, for example, sodium chloride, that is a combination of many. So it's not one sodium and a chloride. It's a combination of a lot of these. But in a molecular formula, you simply could have this ethane floating around all by itself. There's nothing else attached to it. That is one molecule of ethane, and it has a very definite weight, that particular weight. Now, its empirical formula, which we talked about a while ago, would be CH3. But the ratio of a 3 or times 3 gives us this compound right here. So again, there you go. And again, you have to multiply by the ratios. Percent composition is if we want to know how much of a particular atom is in the entire molecule. So here's an example of that for ethane. Again, carbon weighs 12 AMUs or grams, and hydrogen weighs simply 1. So if we're looking at the part of the whole, there are 2 of the carbons, so we're going to do the math on that, which turns out to be 24. Where does 30 come from? Add in 6 times 1. This is supposed to be a 1. That looks a lot like a 2. Scratch that out. We'll just say there, 1. So 24 plus 6 gives us about 30. Divide the part by the whole, multiply times 100%, and there we go. We have our answer. For moles. Moles is a counting tool that we use because this is a ridiculously large number. We'll talk about that in class. So we like to call it just 1 mole. And the neat thing about it is every mole, regardless of what you're talking about, it's a counting tool. It's always that number. And there's some other things we can talk about that with later on. Very interesting. But just like a dozen is always 12, a mole is always 6.02 times 10 to the 23rd. Now the masses, of course, can change. Molar mass, so that's the mass of 1 mole of it. So again, we said the masses can change. It just depends on what specifically you are talking about. Looking at this example, this is again using some dimensional analysis. If I had, as an example, 24 grams of carbon, I could do some math to figure, okay, that's 1 mole of carbon as a formula weight or molecular weight. Not really, just formula weight, of 12, about. So that would give me 1 mole of carbon. And then I could use Avogadro's number if I wanted to, and say, okay, that's going to be 6.02 times 10 to the 23rd, and that's going to be over, again, 1 mole. The nice thing that we're seeing here is if you have moles, moles can take you anywhere. Or if you want to go somewhere else, go to moles, because moles is kind of like your gateway to all other types of measurements. Looking at some of these, it just kind of makes a comparison of different types of substances, compounds, and what their formula weights would be. Empirical formulas. Here's the key to that whole thing. If I give you a bunch of percentages and say this substance has X percentage of X, Y, and Z, always assume you have 100 grams and you're home free. That'll solve the problem for you. We'll see examples of that in class. Here's an example. You have this stuff here, which is found in sunscreen, and we have our percentages. So how do we know what the empirical formula of this substance is? Well, we have to take these percentages and turn them into grams, and then just do the math, and we get these ratios. Now from here, we get stuck. So all right, now I have these moles. What's the formula? Well, we're going to say CHNO. That's just what's kind of told how we're going to go through here. And divide by the lowest value. And if I divide that by itself, that makes this 1. This one goes in here about twice. And these guys, it goes in about 7 times or so. And we'll see how that works out on the next slide here. And there you have it. Same idea. So there's our formula. Alright, I'm going to go ahead and stop here, and we'll pick this up in the next lecture.